Welcome to the session on numerical integration. In the previous classes, we discussed numerical differentiation using Newton's forward interpolation formula and Newton's backward interpolation formula. Here, we shall discuss numerical integration. If f of x is explicitly defined as a mathematical function and if it is integrable, we can evaluate the definite integral from a to b f of x dx exactly. But sometimes the function y equal to f of x is defined by means of n plus 1 paired values xi yi, where I equal to 0, 1, 2, 3, etc. up to n. In such situations, we resort to numerical integration, in which we replace f of x by any convenient interpolating polynomial p of x, and we compute integral from a to b p of x dx, which is approximately equal to this definite integral a to b f of x dx. The process of numerical integration of a function of a single variable is sometimes called mechanical quadrature or simply the quadrature. And that of a function of two variables is called mechanical cubature or simply cubature. Let y naught, y1, y2, etc., yn be n points of the function y equal to f of x corresponding to the arguments x equal to x naught, x1, etc., xn, which are equally spaced with the step size h. The width of each interval is h. Then we have the Newton's forward interpolation formula. Y is equal to y naught plus u by 1 factorial into delta y naught plus u into u minus 1 divided by 2 factorial into delta square y naught plus u minus 1 u minus 2 divided by 3 factorial into delta cube y naught plus etc., where delta denote the forward difference operator. Here u is equal to x minus x naught divided by h. Now, we integrate this y between the limits x naught and xn, that is integral from x naught to xn y dx is equal to integral from x naught to, we can write xn as x naught plus nh y dx, that is equal to integral from, we substitute u equal to x minus x naught by h, which implies u into h is equal to x minus x naught, or dx is equal to h into du. Dx is h into du. Therefore, we have to write this equal to integral from 0 to n, because if x equal to x naught, we get u equal to 0. X equal to x naught implies u equal to 0, and if x equal to x naught plus nh, which gives u equal to x naught plus nh minus x naught divided by h, that is u equal to nh divided by h that is u equal to n. Therefore, the limit of integration becomes 0 and n, y naught plus u by 1 factorial into delta y naught plus u into u minus 1 by 2 factorial into delta square y naught plus u into u minus 1 into u minus 2 divided by 3 factorial into delta cube y naught plus etc. Here dx is u into du, sorry, h into du. This is equal to h into integral from 0 to n y naught plus 1 by 1 factorial is 1, therefore, this is u into delta y naught plus here u square minus u divided by 2 factorial is 2 into delta square y naught plus here u cube minus 3 u square plus 2 u divided by 6, 3 factorial is 6 into delta cube y naught plus etc. du. Which is equal to, on integration we get this equal to h into integral from h into y naught into u. On integration we get integral of y naught is y naught into u plus integral of u is u square by 2 into delta y naught plus 1 by 2 into u cube by 3 minus u square by 2 into delta square y naught plus 1 by 6 into u raised to 4 by 4 minus 3 into u cube by 3, that is u cube, plus 2 into u square by 2, that is u square, into delta cube y naught plus etc. Between the limits 0 and n. Limit of integration is 0 to n. That is equal to h into n y naught. If we apply the upper limit n, we get all the terms containing u. Therefore, if we use this lower limit 0, all the term will become 0. Therefore, we use the upper limit, we get n into y naught plus n square by 2 into delta y naught plus 1 by 2 into n cube by 3 minus n square by 2 into delta square y naught plus 1 by 6 into n raised to 4 by 4 minus n cube plus n square into delta cube y naught. Similarly, if we write the next term, we will get this plus 1 by 24 into n raised to 5 divided by 5 minus 3 into n raised to 4 divided by 2 plus 11 into n cube divided by 3 minus 3 n square into delta raised to 4 y naught plus next term is 1 by 120 into n raised to 6 by 6 minus 2 into n raised to 5 plus 35 by 4 n raised to 4 minus 50 by 3 n cube plus 12 n square into delta raised to 5 y naught. The next term is this plus 1 by 720 into n raised to 7 by 7 minus 15 by 6 n raised to 6 by 6, sorry 15 by 6 n raised to 6 plus 17 n raised to 5 minus 225 by 4 n raised to 4 plus 274 divided by 3 n cube minus 60 n square into delta raised to 6 y naught plus etc. That is integral from x naught to x1, x naught to xn y dx is equal to this. This expression is called Newton-Cotes quadrature formula. This is a general formula, namely Newton-Cotes quadrature formula. From this formula, we can obtain a variety of special quadrature formulas by putting n equal to 1, 2, 3, etc. If we put n equal to 1 in this expression, we get the trapezoidal rule of numerical integration. In this case, we assume there are only two paired values of x and y, or that the interpolating polynomial is linear. Then we get integral from x naught to xn means integral from x naught to x1 if n equal to 1, integral from x naught to x1 y dx is equal to h into 1 y naught, that is y naught, plus 1 by 2 into delta y naught. All the other terms do not exist, because if we are given only two paired values, therefore, all the higher order differences are 0, do not exist. This is equal to h into y naught plus 1 by 2 into delta y naught is the first forward difference, that is y1 minus y naught. Delta y naught is y1 minus y naught. Therefore, this will become integral from x naught to xn y dx, sorry, x naught to x1 y dx is equal to h into y naught plus y1 by 2 minus y naught by 2, that is equal to h by 2 into y naught plus y1. This is known as the trapezoidal rule of integration. Trapezoidal rule. Now, let us see the composite trapezoidal rule, that is integral from x naught to x n y dx equal to integral from x naught to x naught plus n h y dx, that is equal to integral from x naught to x 1 y dx plus integral from x 1 to x 2 y dx plus integral from x 2 to x 3 y dx plus etc. plus integral from x n minus 1 to x n y dx. Where x I minus x I minus 1, this difference is constant h for I equal to 0, 1, 2, 3 up to n. This is equal to h by 2 into integral x naught to x 1 y dx is just derived, that is equal to h by 2 into y naught plus y 1 plus similarly value of this integral is h by 2 into y 1 plus y 2 plus next is h by 2 into y 2 plus y 3 plus etc. plus value of this integral is h by 2 into y n minus 1 plus y n. That is integral from x naught to x 1 y dx is just derived. The value of this definite integral is h by 2 into y naught plus y 1, that is we adding the corresponding y values and dividing by 2, then we multiply by the width of the interval h. This is equal to h by 2 is common, y naught plus y 1 plus y 1 plus y 2 plus y 2 plus y 3 plus etc. plus y n minus 1 plus y n. Which is equal to h by 2 into here y 1, y 2, y 3 etc. are 2 times, y naught is only 1 and y n is only 1. Before this integral, this value, we get one more y n minus 1 here. Therefore, this is equal to y naught plus y n plus 2 times y 1 plus y 2 plus etc. plus y n minus 1. That is integral from x naught to x n y dx is equal to h by 2 into y naught plus y n plus 2 times y 1 plus y 2 plus etc. plus y n minus 1. That is we are adding the first and last ordinates y naught and y n, and we are adding the remaining ordinates y 1 to y n minus 1 and multiplied by 2. This is known as the composite trapezoidal rule. Now, let us see the geometrical interpretation of the trapezoidal rule. Let DC be the curve of the equation y equal to f of x, and let dA and CB be the ordinates of the terminal points D and C of the curve DC. Let OA, here the origin O, OA is equal to A and OB is equal to B. Then this length AB is equal to OB minus OA, that is B minus A. Now, we divide this segment AB into n equal parts A1, A1 A2, A2 A3, etc. An minus 1 B. We just divide the segment AB by means of these points A1, A2, A3, etc. N minus 1 into n equal parts, so that length of each part is equal to B minus A divided by H. Sorry, B minus A divided by n, which is equal to H. We just denote this length by H. Now, we draw the ordinates through A1, A2, A3, etc. An minus 1. And let the length of these ordinates be, this is taken as y1, next is y2, y3, y4, etc. This is yn plus 1. Here yn plus 1, this is yn. Now, the total area is divided into n trapeziums, just like this. Consider this as a trapezium. We just approximate this portion of arc by a straight line. Similarly, the next division also, this is the portion of curve. We approximate this curve by a straight line, then we will get trapezium. That is, the total area is divided into n trapeziums, all having the same width h. Now, assume the respective areas of each trapeziums be A1, A2, etc. An are the areas. Therefore, A1 is equal to, A1 means the area of this first trapezium, which is equal to 1 by 2 into y1 plus y2 into h. Similarly, A2 means the area of this second trapezium, which is equal to 1 by 2 into, here the ordinates are y2 and y3. Therefore, area is 1 by 2 into y2 plus y3 into h. Similarly, A3 means the area of the third trapezium, which is equal to 1 by 2 into y3 plus y4h, etc. An. N means the nth trapezium area is equal to 1 by 2 into yn plus 1 into h. The ordinates are yn and yn plus 1. Therefore, the area of the nth trapezium is equal to 1 by 2 into yn plus 1 into h. Now, we add these areas, we get the total area. Total area means the area under this curve DC above the x axis and between the ordinates at A and ordinate at B. That is the total area is the integral from A to B y dx, that is equal to 1 by 2 into y 1 plus, here 1 by 2 is common and h is also common, 1 by 2 into h, y 1 plus y 2 plus, here y 2 plus y 3, then y 3 plus y 4 plus etc. plus y n plus y n plus 1. Which is equal to h by 2 into here y 2, y 3, y 4 etc. up to y n are 2 times and y 1 is only 1 and y n plus 1 is only 1. Therefore, we write this as h by 2 into a plus 2b, where a equal to the sum of the first and last ordinates. That is, this is the first ordinate y 1 and the last ordinate is y n plus 1. That is a equal to sum of first and last ordinates. And b equal to sum of the remaining ordinates. That is the total area integral from A to B. A to B means small letters A and B y dx, because y equal to A and OB equal to small b. Therefore, integral from A to B y dx is equal to h by 2 into A plus 2b, where A is the sum of first and last ordinates and B is the sum of the remaining ordinates. This is the trapezoidal rule, geometrical interpretation of trapezoidal rule. Here we used the trapeziums. So, this rule is called the trapezoidal rule. That is, the formula for trapezoidal rule is integral from A to B by dx is equal to h by 2 into sum of first and last ordinates plus 2 times the sum of remaining ordinates. This is the formula used in the trapezoidal rule. Now, let me conclude this session. In this session, we just derived the Newton's Cotes formula for integration, which is a general formula for integration, numerical integration. If we substitute n is equal to 1, we get the trapezoidal rule. Thank you for listening this class. Have a nice day.